Thank you very much, and thank you to the organizers for inviting me to speak. It's a really huge pleasure and honor for me to be here. Over the last 5 years or so, there's been enormous progress in the field of ultracold molecules, and that has been happening on two parallel fronts: molecules that are formed by association of ultracold atoms and molecules that are cooled directly. And we heard already from Jun Yi's talk about the amazing progress that's been made in forming quantum gases of polar molecules by atom association, and how those molecules are now being used to study many-body quantum physics. And indeed, we'll hear more about that topic in the very next talk in this session. In my talk, I'll be focusing on laser-cooled molecules and how those molecules can be used to test fundamental physics. This picture here on the title slide was taken with a regular mobile phone camera, and maybe if you look hard enough, you can just about make out this little orange blob here, which corresponds to ultra-cold calcium fluoride molecules. We can see them by eye in the lab. We make these ultra-cold molecules using an apparatus that looks a little bit like this. So we start out by making a beam of molecules by cryogenic buffer gas cooling. We apply some transverse laser cooling to collimate that molecular beam, and then we slow the beam down to low velocity using the radiation pressure of this counterpropagating laser light. Here, the black curve shows you the velocity distribution coming out of the cryogenic source, and the red curve here shows you the velocity distribution when we turn on this laser slowing beam. And in this case, the laser slowing light is at fixed frequency, and we see that the molecules have been decelerated to about 100 meters per second. And now we apply a frequency chirp to the laser slowing light in order to follow the changing Doppler shift of the molecules. And as we do that, as we apply an increasingly large frequency chirp, then you see that we can decelerate the molecules to lower and lower velocities. When we tune everything up just right in the lab, we can make molecules at about 10 meters per second, and that is slow enough for them to be captured in a magneto-optical trap. And here you can see a picture of the calcium fluoride molecules in the MOT imaged onto a CCD camera. We drive the MOT using 4 different wavelengths of light in order to address the 4 lowest lying vibrational states of the molecule. And we measure the temperature of the molecules using the standard ballistic expansion method. And we typically have about 5 times 10 to the 4 calcium fluoride molecules in the MOT. The temperature is about 1 millikelvin, and the peak density about 5 times 10 to the 6 per cubic centimeter. And this is a growing field. It started with strontium fluoride in Dave DeMille's lab, and now we have also calcium fluoride at Imperial, Harvard, and Princeton, yttrium oxide at Giller, and polyatomic calcium hydroxide at Harvard. And you'll be hearing more about that tomorrow. Also, there are many more species that are being worked on and will be coming online very soon, and many more groups that are entering the field. So it's a very exciting time for the field right now. The MOT is a great starting point, but these molecules are not cold enough for most of the experiments that we would like to do. So the next thing that we do is apply sub-Doppler cooling to the molecules. And we do that using the gray molasses cooling method. There are a few different ways to do that. In my group, we actually like to do it in 2 steps. So the first step is optimized. The parameters are optimized for high capture velocity so that we can capture all of the molecules in the MOT and cool them down to low temperature. We typically reach about 55 microkelvin. And then in the second step is optimized for the lowest temperature, and we cool the molecules to about 5 microkelvin. At this stage, we like to transfer the molecules into conservative traps, and in my group, we work with both magnetic traps and optical traps. Here is a picture of calcium fluoride molecules released from a magnetic trap, where we typically have about 10 to the 4 molecules at 100 microkelvin. The lifetime is about 4 seconds, and the peak density is pretty low, about 10 to the 5 per cubic centimeter. Here are calcium fluoride molecules in a 1D optical lattice, where we have about 500 molecules at 50 microkelvin. The lifetime in the lattice is about 1.7 seconds. And because we cool the molecules into the lattice, the density goes up, and we have a peak density about 4 times 10 to the 9 per cubic centimeter. And other groups have obtained very similar results, both in Yale, Harvard, Giller, and Princeton. I also can't resist showing you these beautiful pictures of single molecules held in tweezer traps at Harvard and Princeton, and you'll be hearing more about that work from Loic and Derek's talk tomorrow. We prepare these molecules in a single rotational, hyperfine, and Zeeman state, and we have good coherent control over that internal state. Here's an example where we do Ramsey spectroscopy on the rotational transition of the molecule. It's at 20.5 gigahertz. And we see here these beautiful Ramsey fringes as a function of as we scan the microwave frequency here. And I'd like to emphasize to you that this is Ramsey spectroscopy done in the inhomogeneous magnetic field of the magnetic trap. Okay, that's only possible because we find states in the molecule whose Zeeman shifts are almost identical. So this is a magnetically insensitive transition. In fact, its sensitivity to magnetic fields is 4.7 hertz per Gauss. And we measure in the magnetic trap a rotational coherence time of about 6 milliseconds. Things are even better in the optical traps. Here's data from Harvard showing Ramsey spectroscopy in a tweezer trap, where they measure a rotational coherence time of about 100 milliseconds, or even extending to 500 milliseconds with the help of a spin echo. Of course, we would like to push these laser-cooled molecules to higher phase-space density, and in order to do that, we need collisional cooling, either direct evaporative cooling or sympathetic cooling with ultracold molecules. In my group, we've been studying the collisions between calcium fluoride molecules and rubidium atoms. We make both species together in a MOT and then transfer both species to the same conservative trap, either a magnetic trap or an optical trap, and we've studied the collisions in both cases. I'll just show you some recent data here from the lab where we look at the collisions in a 1D lattice. So here in the top picture, you see rubidium loaded into the lattice on its own, and here calcium fluoride loaded into the lattice on its own. And then we load the two species together, and what you see is that in the place where the two species overlap, the calcium fluoride is ejected from the lattice. That's because in this experiment we prepared the molecules in the first rotationally excited state, and when they collide with the rubidium, they can be transferred to the rotational ground state. That releases a lot of energy, which ejects the molecules from the lattice. So these are inelastic, rotation-changing collisions between the molecules and the atoms. Right now in the lab, we're studying the elastic collisions between the molecules in the rotational ground state and these rubidium atoms. But that's a whole other story, and a story which is currently unfolding in the lab. These ultracold molecules have many applications in quantum physics and chemistry, but what I would like to focus on is their applications in fundamental physics. And since I've just been talking about molecules in a lattice, the first thing that I'd like to advocate is the value of a molecular lattice clock, a clock operating on the vibrational transition of a molecule. Such a clock could be used as a frequency standard in the infra-red, where currently there's actually no good frequency standards. And it could also be used to measure the temporal variation of the electron-to-proton mass ratio, ME/MP. Variations of fundamental constants such as that are predicted by various extensions of the standard model, right, for example, by unification theories and various theories of dark matter and of dark energy. Optical atomic clocks, such as the strontium lattice clock, are not sensitive to ME/MP. And microwave atomic clocks, like the cesium clock, they are sensitive to ME/MP, but their sensitivity, their precision, is ultimately limited because they're low-frequency clocks. So what we would really like to have is a lattice clock that is based on the vibrational transition of a molecule, which is directly sensitive to ME/MP. And in this context, I'd like to highlight a result from 2019 using ultracold KRB molecules that set this limit here at the level of 1 part in 10 to the 14 per year for the variation of ME over MP. And let me also highlight the work being done in Tanya Zelevinsky's group, where they're developing a clock based on strontium-2 molecules in an optical lattice. In my group, we think it could be interesting to develop a lattice clock based on these calcium fluoride molecules. And here the idea is very simple. You just drive the fundamental vibrational transition of the molecule without changing the rotational state. Okay, that's a 2-photon Raman transition with a line width of about 1 hertz. And we think it potentially makes a very good clock, because if all you do to the molecule is change the vibrational state, then hardly anything about the molecule changes. Okay, the properties of the 2 vibrational states are almost identical. And so, in particular, the Zeeman shifts and the DC Stark shifts and the AC Stark shifts, they're almost identical in the 2 vibrational states. By contrast, actually, the rotational transitions are sensitive to all of these things and so could be used to measure the electric fields and the magnetic fields and the lattice intensity and so on. If we put in the numbers here, if we take 10 to the 4 molecules in the lattice, which actually has already been achieved in Harvard, and a clock operating at the natural line width limit, then we would expect a fractional instability of 5 times 10 to the minus 18 in 1 day, which is an interesting level of precision. Now, of course, this vibrational transition is not completely insensitive to the lattice. Okay, so we would like to find some magic wavelengths where the sensitivity to the lattice disappears completely. And here is our calculation of the differential polarizability of the two vibrational states here. And you see that indeed there are several magic wavelengths, including this one out here, where there's a very, very shallow zero crossing, which we think is very good for making a clock. We've tried to estimate the accuracy that we think would be achievable in a clock of this kind. I won't go through all of the details here, but hopefully you can see that the numbers look quite appealing. So we started work in this direction. You've seen already that we have molecules in a lattice. We've actually developed a quantum cascade laser system to drive the vibrational transition directly. And we're starting now to work on this Raman laser system so that we can drive the 2-photon transition. Another way that laser-cooled molecules can be used to test fundamental physics is by measuring the electron's electric dipole moment. And you heard already from Eric Cornell about the beautiful experiment being done at Gila using molecular ions in a trap. Let me just review a little bit the motivation for these EDM experiments and why it is we like to use molecules. Here, this plot shows the predicted value of the electron's electric dipole moment according to various theories. In the standard model, the predicted value is extremely tiny, whereas most theories that extend the standard model predict much, much larger values. Okay, so the green and blue boxes here, for example, are various flavors of supersymmetry. And the current limit has been set by the ACME collaboration using a beam of thorium oxide molecules, and is shown by this dashed line here. Right? Everything above the line is excluded. EDM measurements are spin precession measurements. Here I have an electron whose spin, that's the blue arrow, is precessing around an applied magnetic field due to the interaction of the magnetic dipole moment with the applied magnetic field. And now my electron here also has an electric dipole moment. Okay, the kind of egg-shaped blue blob is supposed to remind you of that. And so if in addition to the magnetic field I apply an electric field, let's say parallel to the magnetic field, then there will be an additional torque due to the interaction of the electric dipole moment with the applied electric field, and that will cause the spin precession rate to change. Let's say it speeds up. And conversely, if I put the electric field in the opposite direction, anti-parallel, then the spin precession rate will slow down. So all you have to do to measure the EDM is to measure the change in the precession rate when the electric field direction is reversed. And now it turns out that the sensitivity of such an experiment is enhanced enormously for electrons that are living inside a heavy polar molecule. Okay, and to sort of give you the cartoon of how that works, in the lab we apply a rather modest electric field in order to polarize the molecule. And then the electron inside the molecule sees this effective electric field internal to the molecule, which is vastly larger than the field that you apply in the lab, and therefore the sensitivity is enhanced enormously in this case. And for that reason, most EDM experiments being done these days use these heavy polar molecules. At the moment, those experiments all use warm molecules, but we think we could make more sensitive experiments, more precise experiments by cooling the molecules down to low temperature. So to that end, we're building an EDM experiment using ultracold terbium fluoride molecules. So far I spoke about calcium fluoride, okay, but calcium fluoride is not particularly sensitive to the EDM. It's too light. Okay, you need to have a heavy atom inside the molecule in order to provide this very large effective electric field. And so for that reason, we like to use terbium fluoride molecules. This is a molecular beam experiment, very much like molecular beam experiments that have been done in the past, with the key difference that we use laser-cooled terbium fluoride molecules. So we make a molecular beam, we apply 2D transverse cooling to this molecular beam in order to generate a very, very highly collimated beam that can travel for a long time without any significant divergence. Okay, and that gives you access to long spin precession times. So we apply the laser cooling, and then the molecules pass through some optical pumping region where we prepare them in the correct state for the measurement. Then they travel through this magnetically shielded region where we apply the electric field, and the spin precession happens. And then finally, we map spin X onto one state of the molecule and spin Y onto a different state of the molecule, and then read out the populations in those two states on these two detectors at the end here. And now I've emphasized to you that the key difference here is the laser cooling. Laser cooling of YBF is more difficult than for calcium fluoride. First of all, the molecule is a lot heavier, and so it's more difficult to push it around using photons. Even worse, the vibrational branching ratios are not so favorable, and also there's some low-lying electronic states in the molecule that arise from inner shell excitation, and all of that kind of complicates the laser cooling scheme. But nevertheless, we try to do it. So here's a simplified version of the experiment where the molecular beam just passes through this region of 2D transverse cooling. There's a sheet of light in the plane of the screen here, and another sheet of light perpendicular to the plane of the screen, so we do the cooling in 2D. And then the molecules travel along a little bit, and finally we measure their density distribution by laser-induced fluorescence detection on a CCD camera. And again, we do that in 2 dimensions, okay? So there's a probe laser in the plane of the screen and another one perpendicular to the plane. Here's what we see on the CCD camera when there's no cooling applied. We just see this cross of fluorescence, which just corresponds to the places where the molecules have passed through these cross probe lasers. And now we turn on the transverse cooling light, first of all in one direction, and we see this bright stripe appearing due to molecules cooled in that direction. And then finally we put the transverse cooling on in both directions, and we see this very bright blob appearing in the center here that corresponds to this very, very highly collimated beam. There's about 10 to the 6 ultracold molecules per shot in this beam, and the laser cooling has increased the beam brightness by at least a factor of 300. We measure the number of ultracold molecules and their temperature as a function of the various experimental parameters. I just show you one particular plot here where we measure the temperature as a function of the magnetic field. We're actually applying sub-Doppler cooling to the molecules here, and I guess many of you will recognize this characteristic behavior for sub-Doppler cooling, where the temperature is minimized when you zero the magnetic field. We have temperatures of about 50 microkelvin, and at that temperature, the molecules can propagate for about 100 milliseconds without any significant growth in the size of the beam. So then if we just take those numbers, 10 to the 6 molecules per shot and a spin precession time of 100 milliseconds, we would expect a shot noise limited EDM uncertainty of 2 times 10 to the minus 31 e-centimeter in a day, which is a very attractive number that keeps us all motivated even when we get tired. Now, So we've applied the laser cooling, and we also know how to do the optical pumping, and we also have good, highly efficient detectors for these molecules. So now the really key parts for us that we need to develop is to develop a spin precession region which is actually suitable for making an EDM measurement. And that turns out to be extremely challenging. It's challenging primarily because our molecule is a magnetic molecule. Okay? It has a magnetic moment of 1 Bohr magneton. That means that we have to measure this extremely tiny electric dipole moment against the background of an enormous magnetic dipole moment. Yeah? And to give you the feel for the numbers here, a magnetic field of 1 femtotesla that correlates with us reversing the electric field looks like an EDM of 4 × 10⁻30 e centimeter. We want to measure much lower than that, okay, so you can kind of see the scale of the challenge that we have. The upshot of that is that we need a magnetic shield with a shielding factor better than 10⁶ in the direction of the electric field. We would like the background magnetic field to be below a picotesla, the gradients to be below 10 picotesla per centimeter. We would like the magnetic noise inside the machine to be below 20 femtotesla per root hertz at the electric field switch frequency. We want to reduce E-correlated leakage currents to below 10 picoamps at our operating field of 20 kilovolt per centimeter. We have to eliminate all ferromagnetic materials from the machine. And we also have to eliminate all metals from the spin precession region because they actually generate too much magnetic Johnson noise. So all of that is very challenging. Let me just show you some pictures here to see some of the solutions that we've come up with. We use ceramic electric field plates that are coated with a thin layer of titanium nitride. And these are actually really great electric field plates. We calculate that their Johnson noise is about 10⁻31 e centimeter per day, which is acceptable for us. They're very flat. They're actually amazing field plates. They can support fields up to 1 million volt per centimeter. We don't need such big fields. We have fields of 20 kilovolt per centimeter, and at that field we measure leakage currents below a nanoamp. This whole electric field structure lives inside a glass vacuum chamber, and all of that sits inside a 4-layer magnetic shield. You're seeing here just the inner layer. Inside this magnetic shield, we measure a shielding factor of 4 × 10⁶ in one of the radial directions. And the noise that we measure is 50 femtotesla per root hertz at 1 hertz, which actually we think is limited by the noise floor of the magnetometers we're using. So hopefully you can see that we're making good progress on this beam experiment with laser-cooled YBF. Looking further into the future, we think it could be great to do an EDM experiment in a trap with these same molecules. An experiment in a lattice. And so to do that, we plan to produce the YBF molecules in a magneto-optical trap and then transfer them to an optical lattice and to do the EDM experiment in the lattice. And this is somewhat new for us, but we've started working in this direction. I'll just show you a few highlights here. One thing that we really need is very, very slow molecules coming out of the cryogenic source to give us the best possible chance of actually loading them into the MOT. Okay, and so normally our molecular beams are moving about 200 meters per second, but now we learned pretty much everything from John Doyle's group in Harvard, how to slow those molecules down to much lower velocity, and we have molecules now moving around 40 meters per second. This is really just using better cryogenics and a more sophisticated design of the cryogenic buffer gas cell. The transverse cooling you've seen already, and here's some very preliminary results showing the deceleration of the molecules using the laser slowing light here. So far just a little bit of laser slowing, but we're on the path, we think, to getting molecules into the MOT here. Finally, let me just say that this is a growing community of people using laser-cooled molecules for measuring EDMs, and I'd like to highlight a measurement of the proton EDM using thallium fluoride molecules, an experiment to measure the electron EDM using laser-cooled polyatomic molecules, and a measurement of the electron EDM using laser-cooled and stark decelerated barium fluoride molecules. So that brings me to the end of the talk. Let me thank all of the current members of the group who have contributed to the things that I've spoken about. And finally, I'd just like to advertise that ICAP in 2024 will be held in London. And we're really extremely excited to be hosting this brilliant conference in this brilliant city. And so we look forward to welcoming you all to London in 2024. Thank you.
Thank you, Mike, for also staying right on time. Pretty good. So the floor is open for questions.
Actually, in your cartoon picture of the EDM, why is the EDM aligned with the spin?
Yeah, I mean, I actually think of that as a consequence of the Wigner-Eckardt theorem. Okay, so you know, if you I can maybe think of a classical picture first of all. So if you think about, you know, an EDM which is orthogonal to the spin, and the electron has a spin, and so I think of that now as, you know, precessing around the direction of the spin and time averaging out to zero. And also, you know, if you just apply the Wigner-Eckardt theorem, you will see that the EDM has to be parallel to the spin.
Okay.
Hi, over here, to your left. So thanks for the talk. Often in these molecules, the hyperfine structure from the ligand can be unresolved in the excited state, and this gives you headaches. Can you talk a little bit about your state prep scheme and how you're dealing with like sort of destructive interference that may arise from these unresolved hyperfine structures?
Yes, thank you. Yes, so our scheme for preparing the EDM state is a stirrup scheme. And indeed, in YBF, the excited state has some unresolved hyperfine structure, and that to some extent, spoils the stirrup scheme. Actually, it's not that bad. Okay, we think we can get sort of 80% contrast even with unresolved hyperfine structure. But yes, indeed, there are schemes where you use a kind of double stirrup scheme that enables you to avoid this problem of the small hyperfine structure. I think it's probably sufficiently complicated that we need to talk about it later.
Where? Oh, John. Oh, okay. Well, there's someone there, but Bill first, and then we go there.
So my question doesn't really matter, but I'm curious. You mentioned that hyperfine clocks would have a sensitivity to ME over MP. So I presume this is because of the fact that magnetic moments of electrons and magnetic moments of protons are different by and large by a mass ratio. But the fact is that the proton magnetic moment, the magnetic moment of any nucleon, is way different from the Dirac value. Whereas the electron moment is almost exactly the Dirac value, you know, within a part in 1,000. So what I'm wondering is, if we could make a hyperfine clock, would we have any prayer of interpreting that in terms of what it meant for ME over MP from the theory of magnetic moments of nucleons?
Yeah, okay. I mean, I guess the first thing I should say is that those measurements have been done already at PTB by comparing the cesium standard with the strontium lattice clock. Okay, so the strontium lattice clock has no sensitivity. The cesium frequency standard is sensitive for exactly the reason you mentioned. It comes through the magnetic dipole moment. So those measurements have been done and do already set the best limits on the time variation of ME over MP.
Right, but how do we know? I mean, is the theory of
Well, I think you're exactly right that people would say that that those experiments are model dependent. Okay, you need some model of how ME over MP comes into the ratio of the magnetic of the dipole moments of the two species, and so you sort of you have to interpret the outcome of the experiment using some kind of model of the nuclear physics of the magnetic moments. this, in one way is why the molecular measurements may be preferred. The molecular measurement, a vibrational transition in a molecule is just proportional to the square root of the of ME over MP. It's an absolutely direct measurement, and so in that sense, it's model independent,
very
and
clear,
that's preferable.
Yeah. Now, since I'm holding the microphone, I got one other question that is
am I.
almost unfair, but as we know, all right-thinking people believe that the only thing you should be looking at for looking for a variation in a fundamental constant is a dimensionless fundamental constant. But I'm pretty sure that both of us know people who seem to be otherwise intelligent people who claim that they could measure the time variation of something that's got units. Would you care to comment?
Only to say that I agree with you that the right-thinking people prefer to measure the variation of dimensionless constants. To me, the only thing we ever measure is ratios of anything, and so I'm not even clear, how you even do an experiment where you're not measuring a dimensionless ratio ultimately.
Exactly, but you know that there are people who...
I do know, yes, but I don't think I can comment on their thinking.
Well, I was wondering whether maybe you could had more of an insight than I do. Okay.
Thank you, Bill.
Yes, thanks.
Yes.
Thanks for the talk. Did I see correctly that you need a 17.5 terahertz laser to drive one of the transitions? Okay, if so, do we call that a taser? And seriously, how do you make a 17.5 terahertz laser?
Yeah, so you did see correctly. We actually have two methods to drive the transition. Driving it directly, which is at 17.5 terahertz. For that, we've actually collaborated with the group at LPL in Paris, who provided for us a quantum cascade laser, which is operating at exactly that frequency. And so that laser is in the lab and is working very nicely. You get a milliwatt or something. That's actually not at all the best way to drive this transition, because when you drive directly like that, you have to change the rotational state, which is not what you want to do at all. So that's a kind of preliminary experiment, so we know roughly where the transition frequency is. Yeah, and then we would go ahead and do the two-photon transition, which is really the right way to do it.
One last question in the back. Microphone is coming your way.
So a common shift that one has to worry about in atomic clocks is just the shift induced by the clock light itself. So for a Raman transition, I would actually have thought that you're even more sensitive to this because you're being dressed by the intermediate state. Is the sort of fractional shift associated with that a lot worse than a single photon clock?
We've estimated, I don't know whether it's in my table, see if I can go back far enough. We've estimated the shift due to the Raman light. So actually what you really want to do again is find a pair of magic frequencies for the Raman light. And yeah, it's in the table here. So it's actually very, very small for the particular pair of wavelengths we chose to use. What we're actually planning to do is to use the lattice light as one of the Raman beams. Yeah, so it's kind of already magic, and then you can find, and then you close the Raman transition with another wavelength, which it turns out you can also make magic, and also requires, a very, very tiny intensity because the lattice is so intense.
John, did you have a question? Yes. Okay, go ahead. Yell.
So to repeat John's question, John thinks that the table here of uncertainties is probably conservative. I guess I agree. I like to be conservative in doing these things. Actually, I find the DC Stark may be a little bit worrying, that it's possibly quite difficult to know the electric fields to much better than than this value. So that might be the, deep in my heart, my biggest worry.
Well, that's it. So thank you, Mike, for an excellent talk.